Right. So since this is a workshop on electric phase transition, I thought I would dig out some, not that old, but sort of stuff that's been lying around for a while since we worked on it 3 years ago, say, and we've started working on it again recently, and I'll tell you why. It's called electric biogenesis, and some of you will have seen some of it, and some of you will have seen lots of it, and Arthur has even been initiating it originally, though I will say something slightly different. The nice thing about this workshop, of course, is one can sort of skip some of the introductory stuff that one might otherwise want to do, and one can talk about some of the nitty-gritty stuff. Well, that's what I want to do, I suppose. So last week we had a morning discussion session where I said something about the zeros and winding and stuff, and there'll be some of that again, but I'm going to take a slightly different perspective, slightly broader perspective, I think. So, if we do electroweak physics and we're into the phase transition, usually what we're interested in is, in fact, baryogenesis when we talk about the phase transition. Of course, the bubble walls and all that stuff is interesting in itself, but I think many of us are motivated by electroweak baryogenesis. So let's just recap what it is we need for baryogenesis. So in the standard model, which is what I'm going to be interested in, with a tiny extension, we have breaking of CFP, just because fermions and gauge fields couple only to the, so the gauge fields only couple to the left hand of fermions. And then there's CP breaking in the CK matrix, and it's a bit complicated. The CK matrix is V guy, and it's somehow composed of some rotation matrices, which take a diagonal Yukawa matrix and put it into the way fermions couple to the Higgs field. It's not so important. But anyway, there is this matrix, and in this matrix are some mixing angles called theta 1, 2, and 3. And there is a CP validating phase, there's a complex phase, and the phase is called delta. And one way of thinking about the strength of the CP validation is to construct this Yarscott invariant, which in the standard model is about 10⁻⁵. And, well, it's been measured by now quite well, so we know all about that. So I'm going to think of it as the strength of the CP validation is somehow encoded into this guy times something else, which I'll tell you about. And then we need to break baryon number in order to do baryogenesis, baryon number conservation. And I'm sure most of us know, if you have a gauge field background, and you have some fermions on top of this gauge field background, then there's an anomaly which connects the baryon number change in time to the change of a particular degree of freedom called Transamin's number, in that movement in time. And which will be important later on is that this Transamin's number is the integral over everything of f contracted with an antisymmetric tensor. So this is actually f dual. And we'll come back to that. So basically, well, in principle, you could have the gauge field moving around, but without necessarily changing the value of this particular quantity, which is this particular observable. But if this one also moves in time, then baryon number of the fermions on top of it will change as well. And that's the point. Okay. Then we know that the electroweak sector has is in a symmetry breaking minimum. It has a web. The Higgs has a web, and we interpret it as the theory having a phase transition between a high temperature phase in which the average of the Higgs field is 0, and a low temperature phase in which it is not. So it's something else, which happens to be 246 GeV. In the appropriate way. So there is a critical temperature above which the symmetry is restored, is the phrase. So the VED is 0. And then there is a low temperature phase, let's say temperature 0, where the VED is 246. At sort of intermediate scales, so temperatures between this and that, you would have an effective temperature dependent VED, which is somewhere in between 0 and 246. And the point, of course, is that if it's a first order phase transition, this changes discontinuously, and if it's a second order phase transition, it does not change continuously. Right, then we can define, if we're particularly interested in this Chern-Simons number observable, then we can define something we can call the diffusion rate. So if we calculate the average of the Chern-Simons number squared and subtract the disconnected bit, Chern-Simons number average squared, and then this if it's in equilibrium, we'll think of this as diffusion, and diffusion has a particular rate, which would be the time derivative of this object. And we can call it the Svalron rate because we know something about Svalrons, which I'll tell you in a minute. But this quantity is the point is if it's in equilibrium and this is in fact diffusion, then this is just a number which is constant in time. And this number turns out to be dependent on some constant, and the VEV function of the temperature divided by the temperature. And it's pressed by whatever the value of V is at a particular temperature. Now potentially this symmetry breaking could be out of equilibrium, but what we know is that in the standard model it isn't. So these are the things we all know. The Bernoulli friction is not first order, there are no bubble walls. Okay, we still do the transition somehow from high temperature to low temperature, and that is a result of the temperature decreasing in time, and that is because the universe expands. So the expansion rate, which is the Hubble rate, is too small to make it. So there is a quench, but it's just a very, very, very slow quench. So everything stays in equilibrium. Now, baryon number generation, because we're in equilibrium, this is mediated by these Svalrons, which are these field configurations that sit halfway between integer values of Chern-Simons number. I'll show you that in a minute. And so if this turns out that this Chern-Simons number, if it's just diffusion equilibrium, this restores and maintains the symmetry of the three baryons and antibaryon. And then the idea is that even if that would not be the case, if you would take the CP violation in the standard model, it would be much too small to account for baryon symmetry. So, well, he's written many papers about this, but this, I suppose, is one of the first ones where he writes down this effective CP violation. So as I said before, so some quantity which encodes CP violation could be this Yarlskov invariant. And then you have some products of sort of, so there's all the quarks here, they have these masses. And so you take the U minus the C and the C minus the T and the U minus the T multiplied by each other, and then you take this with that and this with that and this with this, and that gives you a total mass dimension 12. And then you must divide it by some mass scale to the 12th, and that's temperature. And this is tiny. This is 10 to the minus 20. Very small. So finite temperature, CP violation is much too small to account for the symmetry, even if you were out of equilibrium. But, is then my point. If you believe that the inflation actually took place, and I think that's probably quite the case, then there must be somewhere an extra scalar degree of freedom, which may or may not be fundamental, but let's for the moment assume it's fundamental, and it will be called an inflaton. So, if you want the energy of inflaton to end up in the standard model, so we want the universe to not be cold at the end of everything, this inflaton must be coupled to the standard model degree of freedom. So the proposal is that one could trigger this quench not by the expansion of the universe, but by an inflaton coupling to the Higgs. Now this is going to work if we want to do this. So we want this quench to be triggered here. They want to be fast. Right? So then we don't want, that's because we want to go out of equilibrium. But then we don't want to go back in equilibrium at a high temperature, because then the Svalrons would wash out the symmetry again. So we need a reheating temperature which is below Tc. Preferably quite a lot below. Okay, so then the statement is that if you're in a fast quench, you're not in equilibrium. And so the transitions that change Chern-Simons number need not necessarily be associated with the Svalron configuration. It's more complicated than that. What instead turn out to be the case is that there is an asymmetry, but it comes from the gauge evolution, which is CP biased. And not in terms of Svalrons necessarily. So is it in fact something with, I'm going to say something about biased diffusion, you can sort of recast it in that language. Or sort of out of equilibrium diffusion, I'll show you that. So the point here is now that you have this baryogenesis, extra baryogenesis, during electroweak reheating. So usually you have preheating or reheating at a very high scale, you have electroweak reheating at a much lower scale, and in between you have equilibrium. So you know that the reheating is out of equilibrium, So now I have moved this to coincide. So there's no period of equilibrium at high temperature in between. You just go straight from inflation to the broken phase. So temperature turns out to be somewhere between 0 and 50 GV, depending on the coupling. And then one of the claims that have been made recently is that the CP violation is in fact not very small at 0 temperature. And that's why there is a chance that it could actually work. And it's basically because this guy, if you're at 0 temperature, well, you can't put 0 there. So what do you put? What's the other mass scale? Well, it's the VEV. If you put the VEV here, that cancels out with the VEVs up here. So then you have your cover coupling. That's still very small. What I'm going to argue is that this form does not. This form is probably correct at high temperature, but at low temperature it gets more complicated, and it's not that small.
How do you know that? I mean, you probably know it more precisely than this. I mean, if you imagine that you put, say, a pi times t instead of t, or pi times VEV instead of VEV, pi times 12 is already a large number.
Yeah, this argument came from an order of magnitude. I mean, this is a dimensional argument. So this is all order of magnitude. The actual calculation you get the right. Nobody has done it at finite temperature. But at 0 temperature you get it out with all the pi.
So how do you get around the Yukawa difference squareds? I mean, it must be...
What turns out is that you have Yukawas in denominators as well. And so if they're small, they cancel out.
Right, but you still must have, if one of the mass differences goes to 0, the effect...
Sure. So you can't allow them to be the gender.
Right.
So at the end, it's going to be... Yeah.
Huh.
Indeed. So right, so I mean, if they're degenerate, the mixing magnitudes go to 0. That's not allowed. But I suppose, I mean, they are what they are. So let me just say something about preheating. So now I have put my baryogenesis at the time of reheating. So there are 3 types of reheating currently that we consider typically. So reheating is usually what you would call when you have perturbative decay of the inflaton. The inflaton comes down, it oscillates in its potential, and decays in sort of perturbative particles. And I'm not sure whether these are the precise correct, but this is around that time when people came up with this sort of thing. And it's these people in various permutations. Then, 10 years later, some of the same people came up with that if the inflaton oscillates, you can also have resonant preheating, non-perturbative particle creation in the standard model. So it's not decaying in strictly sense. It's just the fact that the oscillation drives particle creation in whatever is coupled to it. It's called resonant preheating. Well, it was originally called preheating, but then later on somebody came up with tachyonic preheating, so we had to call this something else. So now it's called resonant preheating. Tachyonic preheating is precisely what happens if you have a fast symmetry breaking and the Higgs field rolls off the hill. These guys came up with it. And it's funny, this guy seems to know Lindis and to be involved in everything. It seems that quite a lot of people decide to be in on this game at the same time. Yeah. So, okay. There are these 3 types, and we're going to be interested in these guys, and particularly this guy right there. So this is, of course, nothing that we came up with. So, well, originally I was going to say that this was the first paper that suggested to do electric baryogenesis in preheating. Not actually true. So in resonant preheating, so they had come up with resonant preheating, and then they discovered, well, actually, if you have this preheating, if you would do it at electric scale, you could boost the Higgs field with large capacity numbers, and they would drag the gauge fields along. And then you could imagine having what I would call CP-biased out-of-equilibrium transition number diffusion. So there would be a diffusion rate type thing, which could be then biased by CP violation. And they came up with that this might in fact work. Actually, before that, there was a paper by Churov and which employed this tachyonic transition. Now, at the time they wrote this paper, the phase transition was considered to be first order. So they mentioned that they have first order. In the bubbles, they then have this tachyonic transition where things just have this fast approach. They don't actually use the bubbles for anything. And later on, R2 and his collaborators just took away this. There are no bubbles. You don't need bubbles. You just have to do this symmetry breaking equation. And in that case, the assumption was that you have this Kibble mechanism, which R2 spoke about, where you have some causally disconnected patches, and they have different values of the winding of the phase, and then when they sort of afterwards reconnect, you discover that there are some defects and things wind around various points. And that would generate a symmetric distribution of textures in SU2 Higgs in 3 dimensions. The defects, the interesting defects, are these textures which are not localized, but sort of winding numbers spread out over 3 dimensions. And then these textures, they can then unwind asymmetrically on this p-valation. I'll say something about that. Now, this unwinding was then actually studied by these guys, where they take such textures and then they see how they unwind on a CP violation, and they find that there is in fact an effect. And I think, I'm not sure, you just had a parameter, right, for the asymmetry, some epsilon, and then you found that if epsilon is bigger than something, then it works. Okay, what I'm going to argue now is that it's in fact tachyonic, but the effect that happens is what it says over here. Right? So what actually happens is that if you have a tachyonic transition, you get large interpolation numbers, you get large gauge fields, and you get CP bias directly into Chalmers mode for diffusion. But you don't actually get this stuff. Well, you do, but it's not important. So it's still tachyonic, but I've taken all the points over here and put them over there, because that's actually what happens. And this was something we've been working on for quite a while, and these guys have done it too. Now the argument being that, okay, why couldn't you have both? So if the T reheating has to be less than the T critical, the TC. Now if you take the energy you have in the potential of the Higgs field that it rolls down from, and you distribute it over the degrees of freedom standard model, you discover that if you want to be below the critical temperature, there's not much room to add extra energy from some inflaton with large kinetic energy. And so the inflaton cannot be dominant in energy. And then what you discover is that tachyonic energy transfer happens during the first rolling off, whereas the resonant happens over several oscillations. And so the energy transfer is faster. So there's no time for having lots of resonant preheating. So it's not resonant, it's tachyonic. The mechanism turns out not to be Kibble. Yeah. So everybody was right, which is always a good resolution.
So the point is, during this fast roll-off is when you produce this large occupation number of Higgses?
Yeah.
Okay.
Yes. So this is what comes here. So at the beginning of the roll-off, the effective potential is, well, the potential is just minus mu squared pi squared. Because the nonlinear coupling, the quartic coupling hasn't kicked in yet. Now, if you solve the Planck-Orn equation for this, you discover that you have modes that grow. So this is an imaginary mass. So you just get, whenever k is less than mu, this guy is growing exponentially. And the occupation number is that squared. So, in the beginning, you have exponentially growing modes for the Higgs field. Now, they're coupled to the gauge field, and then you can go and ask numerically, does it also lead to large occupation number of the gauge field? And this is this plot. This is the occupation number of the gauge field, log scale. And you start out having nothing, and then these are the unstable modes. They are being populated. And then they begin scattering with each other. So then they kick up the ultraviolet tail up here. And you have occupation numbers that are between 1 and whatever, 100, which is quite good. And then they settle. These are for different times. So you end up with some not thermalized, but almost stable spectrum. And then in the long run, you will start thermalizing the ultraviolet.
So what cuts off the modes? I mean, they grow exponentially with T, and then at some point
they stop.
They stop.
Well, so there's nonlinear interactions. It's back reaction.
Back reaction.
That kicks in sort of, well, it started here already, right? But it sort of comes here. the time between that and that is the same as between this and this. So it sort of kicks up its tail. And then nothing much happens for a long time.
So this is the Higgs field.
This is the gauge field.
Oh, this is the gauge field.
In
Gauge field occupation.
Coulomb gauge, I think.
This is very similar to the plasma instability
Very much so.
feature in the heavy ion type calculation.
Yes. Yeah. The argument is that when you get to here, you already have stabilized your, for instance, your equation of state is already what it should be, even though it's not thermalized, for instance. So if you would look at heavy ion collisions, you would see the equation of state already at that time. Okay. Now, a posteriori, you then conclude that large occupation number is the same thing as classical effect dynamics, which means that your classical simulation you did there is actually a good thing to do. And you get the energy goes from the Higgs to the gauge field. So now the point is that now I've pumped energy into the gauge field. The question is the Chern-Simons number degree of freedom moving as well? Or is it just, you know, B fields and E fields and things? So Chern-Simons number is E dot B. It's not obvious that that would also be excited by this, although it is. Right. So, in order to tell you what non-equilibrium diffusion is, I have to tell you what equilibrium diffusion is. So, as you probably know, the vacuum, the gauge field, well, the Higgs gauge, I enumerated by this Chern-Simons number. Chern-Simons is integer in all these minima. And so if you want to change Chern-Simons number, you have to go from one minimum to the next. And the way to do that is to go above, well, other you can quantum tunnel, but that's not what we learned here. You can sort of go over this guy. And if you want to calculate the rate, well, the rate is controlled by the Boltzmann factor of whatever configuration sits on top here. Chern-Simons number half. And that's called sphaneron. And it has some energy. But if you're at high enough temperature, so this is broken phase, but this is very high. If you're on the symmetric phase, the potential looks, well, it still has this general shape, but it's much lower. And various coefficients are different, but it's somehow the same feature. Now, in those vacua, the Chern-Simons number is equal to the Higgs winding number. We'll come back to that, and it's integer. So if you want transition, it goes to the sphaneron, and then that means the rate is suppressed by the sphaneron energy. And these very clever guys have, over many, many years, calculated this in symmetrical broken phase, and I think sort of the ruling paper at the moment is you and Guy and Dietrich, isn't it? 2001 or so. I think that's the So there is a coefficient in front of this t to the 4 exponential of the sphaneron. And that is known very well. Not clear to me exactly. So Chern-Simons number is plus minus a half in these guys. I'm not quite sure what the winding number does. I mean, it goes from 0 to 1 somehow, but I'm not quite sure. I would like to talk to them about that. Certainly, it also changes by an integer, and they go together. Chern-Simons number and winding numbers, they sort of do the transition together. In a sense, it's a dressed winding, dressed by the gauge field, which is why the energy is the lowest. Is when they're dressed. But now, of course, this diffusion, this Chern-Simons number has no actual, it doesn't refer to winding number. It's just because we happen to know that the vacuum has the winding number equal to the Chern-Simons number. So, even when it's not, strictly speaking, diffusion, you could calculate this object, the time derivative of Chern-Simons number squared minus Chern-Simons number average squared. Let's call that diffusion rate. An effective diffusion rate. It's now time dependent. And then the question is, can the Chern-Simons number mode change in time? So this is a picture of this Chern-Simons number squared minus Chern-Simons number squared. So it starts at 0, and then it grows to something, and then it sort of peters out. And this is during this transition. So the Higgs field goes from 0 to something, ends up at the bed, and then the Chern-Simons number moves as well, squared. Right? So here there is no asymmetry, but there is an effective diffusion rate, which would be the time derivative of this guy. This is for different speeds of the transition. I'll get back to that. Then you could try to do something like linear response to a chemical potential. If you had a chemical potential for Chern-Simons number, you would expect that the baryon number would change in time. You would have this diffusion guy, then you would be this effective chemical potential divided by effective temperature, which I've also mentioned later. So if you want the barrier number, you integrate this over time. And if this guy, these guys are also time dependent, you just integrate over everything and see what you get. And the question whether this is a good picture of what's going on. Now, you could try to use this Fallon rate here. That would probably be wrong, because this doesn't look like, this is not a constant. So that's one thing. The other thing is this asymmetric texture unwinding, which these guys worked on. So a texture in a scalar theory, well, it's not in a scalar theory. Texture is an unlocalized. So it's an integer winding number, but you can still think of it as something called a skirmion. Skirmion is localized sort of by hand, but it's still somehow sort of a hedgehog with arrows pointing out in all directions. If you have gauge fields around, as well as the scalar, the analog is to have Chern-Simons number not equal to winding number. So if they're both integer, but they're not the same, you can always gauge transform them so that A is just 0 and this is just an integer. And then it's one of those. It's like having your gauge field. So if they're not the same, you effectively have a texture or a skirmion. Okay, in principle, if you have such a transition, these guys are created through the Killing mechanism. They'll start out being these localized lumps, and then they will sort of smear out over time, unless they're stabilized. That's another good question, whether gauge stabilized skirmion is stable. They are by a vector field, right? I don't know about gauge vector field. So if you have a massive vector field coupling to them, you can integrate out that one, and then you get the skirm term. So the idea of this would be that you start with a CV symmetric set of skirmions from the Kibble, and then they start adjusting the winding number to the Chern-Simons number, either by moving Chern-Simons number or winding number. And that turns out to depend on the size of the skirmion, and there is some cutoff of the size where it goes one way or the other. Now it turns out the CP violation, we should use that, it shifts this critical size, and that depends on the sign of the winding number. So, and that gives a net symmetry. Right? There are more winding one way or the other way depending on what the sign of this is. So you get the symmetry. And this was what these guys figured out by just simulating one of these things and putting it into violation and see what happens. And yeah. So that's your epsilon. Right? That's whatever that is. Okay. So let's go to what I did, or we did. So I want to take a standard model, and then I want to cut away all the bits that I'm not interested in. So I'm going to throw away all these gauge fields that I don't want. So I have SU2 left. Then I don't want to do the fermions, so I'm going to integrate out the fermions. Now I'm going to make a gradient expansion. Then I'm going to take the leading order, and I'll tell you why that wasn't a very good choice, but never mind. It'll give us the general gist of what's going on. So the nice thing about this is that, as you can see, this is f of dual. So this thing is like Chern-Simons number with a chemical potential which is phi squared. Except that phi squared is now space and time dependent. But if I would take the average here and put it outside, you would have a chemical potential for Chern-Simons number. And that's why it gives this asymmetric diffusion. Now I don't want to do the inflaton, so I'm going to replace this coupling between the inflaton and the Higgs by a time dependent mass, which is going to start at plus mu squared and go to minus mu squared when t becomes tq. Then it's going to be constant minus mu squared for the rest of the time. And then I'm going to restrict my Higgs mass to be something. But there's nothing other than practical reason for doing that. Right, so that's my standard model. It's SU2 Higgs plus CP violation. There's a strength here, which I'll put in later. And then there is a time dependent mass squared. Okay, so now you do the simulations, you solve the transparent motion, you average over in-chill conditions. Okay, so what you see is that the Higgs field falls down, this guy, and it damps and it goes into the BEV, the finite temperature level. Then, what you see here is now the Chern-Simons number moves first. This is the red line. It goes up, and then it goes down, and then it ends up somewhere here. And then afterwards, the winding number moves. here, and then it goes down and it stays constant. And at the end, if you run much longer, you discover that this guy then eventually goes to that guy. Now, so these are the barriers, right? Barrier symmetry. Winding number tells you what the Chern-Simons number is, tells you what the barrier number is. And the thing is that the place that this guy moves is at the minimum of the Higgs field here. There. I don't know whether one can argue that there is a bump here as well, but anyway. If one is very brave, one can say that something happens whenever there's a movement. But most of it happens here.
So you're saying that the first time when the Higgs field reaches the maximum, it doesn't have any winding numbers?
Next. This is averaged.
Oh, sorry.
Mm.
Yeah.
Mm.
Where does this step in the winding number come? I mean, I don't...
It comes...
Suddenly it jumps.
Yeah, it comes here. So I'll explain that. But so the thing is that here, winding number would like to accommodate Chern-Simons number. And it discovers that, it's far away. So it wants to move towards Chern-Simons number, or the other way around. But the problem is that it can only move through zeros of the Higgs field. And there are no zeros of the Higgs field here. But there are here. And that's why it moves there. There's delay. And that's why it can again try to move here and here and here. But there are less and less zeros. And eventually there are no more zeros.
It's very small, the winding number anyway. I mean, deviation from zero is
the average is quite small.
So that you have plus ones and minus ones.
Is
Is this divided by the volume or?
Yes.
But yeah,
No.
this is an average over several runs.
It's average of 100 runs.
I see. Yes.
So you have 1s and 2s and 3s basically.
So is it biased to negative or is it?
Yeah.
So or is it just random?
Which way it goes?
Yes.
If you have, there can be the occasional flip to the other side, but once you turn side, your CP violation is large enough, there are only flips to one side. If you would have no CP violation, you would have flips to both sides.
So the CP violation drives the Chern-Simons number to negative, and then the winding number wants to follow it.
Yes. However, the weird thing is that if you would do a linearized theory, you would get this bump, which is to the opposite side. So it's quite crucial that this guy can then go down there. And if I would have chosen a different Higgs mass, it would come back up again. So it's not so simple. But once you have generated a Simons number, then this guy wants to move, and it has to wait until this happens.
So why don't you see secondary bumps then when?
You mean here?
Yeah.
Yeah. So they're very small.
They're there, but
They're very small.
Why does the Chern-Simons number? Why do the Chern-Simons number, the winding number? Why do they not?
They do eventually. So
you see that in the simulation.
Yeah. Winding number. Yeah. In the individual configuration. The winding number has to be integer.
Yeah.
Whereas these guys can sort of slosh around. And I think that's why there was this. If you run
long enough time.
So we did one of them when we ran to 500, and then eventually we go there. Although actually, I could imagine that this asymmetric unwinding could begin kicking in here, in principle. Now, if you don't have any zeros sort of handed to you, for it to unwind, that takes a lot of energy. So it's very unlikely that it would happen. But in principle, if you would wait, in principle, one of these could flip to the other one. I wouldn't rule out that you could have this mechanism later on, but I think it would be very small.
Yeah. So how do you know that the growth in the Chern-Simons number is not the asymmetric unwinding? Because it's not because you are. In order to see whether there is something unwinding, you can't just look at the average. You have to look at individual.
So there are two. So first of all, this thing you can reproduce by just doing a linearized equation of motion. So this bump, that just comes in the equation of motion. And it's because you have the bias in the gauge equation of motion. It makes no reference to the Higgs. And then, let me show you. Because now, if you now do this asymmetric diffusion thing, so now because the Higgs oscillates, so the effective chemical potential is this black line here. And the effective diffusion rate is this red line. And now you do this convolution thing. And you get this blue line. Right? And the red is the simulation. So it suggests that this is in fact just that. You have a bias for Chern-Simons number, which is the chemical potential, but because the chemical potential changes sign, right? It's the derivative of Higgs squared. Then you get a chemical potential which changes sign. And that's why it first goes up and then it goes down. And of course, these guys are correlated, or they're anti-correlated, because of how dynamics are. And that's just why. So I think, yeah. So I think that's what's happening here. Right. And then, yeah. And then you find that you have this Chern-Simons number and the winding one wants to move, but it can't until you get to here. Because then you get thrown lots of zeros at it, and then it just unwinds.
So in that plot on the right, the different green lines, what are they? Are they?
They're for different values of the CP violating, but all rescaled to 1.
Yeah.
So these guys are completely proportional to delta CP.
So you have a plot for a single run of the winding number.
Not here, but yes. So
How does that generally look?
well, so in the beginning it's right, because the operator is wild.
Yeah.
And then, so, well, yeah, so it's...
Then the Higgs reaches its maximum. You should have a well-defined one.
Yeah, yeah. Yeah, so Chern-Simons number, so it's actually hard to see this in the Chern-Simons number. That's an average effect. I mean, this bump. But Chern-Simons number goes to somewhere, and then the Higgs follows along. And yeah, I think that's true. So what we did actually simulations with plus and minus delta CP. And then we compare. And some of them have a flip. So the average of, say, 2 runs, you should be able to, you see this comes out. You have to choose what this T effective is supposed to be. You can estimate it or you can fit it. I think we fit it to get this height correctly. Then the rest follow. It's supposed to be an effective temperature in infrared modes, which are the ones that are important. So for instance, you could take the effective temperature in all the unstable modes, so then you get a few hundred GeV. And of course that's why you do have things moving, right? Even though you have very low energy. Okay, so this is what I mean. So I don't mean diffusion in any sort of statistical sense, apart from the fact that I use this quantity, which just grows because you're pumping energy into the degrees of freedom. So we're gonna so we did a test in 1 + 1 dimension. So you can either do, this is exactly the same, 1 + 1, simpler system, you can do more things, just to the complex scale. Here, we have a random initial condition for the Higgs field, with phases and everything. And then you end up there, and if you do it without any phase in the initial condition, well, things are crazy here, but you end up in, it's the same thing. So that presumably there's no cable going on there. And then it moves, to just when you get to the minimum, it moves to accommodate the Chern-Simons number.
You say that if you don't mean no CP violating phases. You say no phases.
And no phases. So to do the kibble, you just need, so it's a complex scale.
Yeah.
So if they have phases, then you get the phases in different cases, and then you get defects. They're not CP violating. I mean, it's a phase of the field.
Okay.
That's the ones that distribute differently in domains.
Yeah.
And so this is just chosen to be
Oh, I see.
like having unitary gauge. So. And then you. So that's what happens there.
So is this now average? Or
This is also average. Yeah. Actually, no. This is a very, very large volume, I think. Actually. But we checked with very large volume and it's the same as average. So of course this is one dimension you shouldn't take completely seriously, but it's the same thing. Oh, by the way, as you can see, the p-relation has the opposite sign for no other reason than just has.
No, but sorry, can you go back? So, I mean, if it is just a single one. Oh, sorry. Yeah. So the binding number is, of course, yeah. So what I'm just wondering is, if you just have random initial phases, then you do by Kibble mechanism, you do get windings.
Yes.
And even on the left, in that plot, the binding number is practically 0 during the first.
On the average, yes.
But that's because you produce
Many.
lots of pluses and lots of minuses. Yes.
I think this is a, I don't know, is it 10,000? That's a size. Okay, so that, by the way, you know, of course there will be a population of defects. It's just that, and they may have this asymmetric, but it seems that it's not what wins here, at least. So, this is the thing about these zeros. So let's plot, this is just a histogram of the value of the Higgs field. Value of the Higgs field at different, so this is the first dip in the Higgs field, this is the second, and the third, and the fourth. This is for different speeds of the quench. That's, yes. So the quickest quench, so this, you know, the first minute we have all these zeros here. And they're the ones where the winding can happen. But if you quench really slowly, which is this guy, then you don't get any zeros. So then you can't make a larger symmetry. And that's why you don't want the quench time to be slower than 20. Because then you get no zeros and there's no symmetry. And I mean, there are some in the subsequent minima, but it's not. That's why there's no extra bump. It's a very small bump. Because you can't move anymore. Yeah. So that's the interpretation. Then you can just show the plot. So now you vary CP violation. You discover it's linear. These are different values of the Higgs mass. Opposite signs, but otherwise they are linear. And you can get the slope, and that tells you the simulations are done with much larger CP violation than you need. So you need to interpolate to somewhere here. That's the argument. Then you can do quench time. This is this linear, whatever this, biased diffusion for different quench times. So again, you have this, the full lines are the simulations, and the dashed lines are this diffusion approximation. So it works quite well until you get to somewhere there, and then it doesn't work anymore. But it tells you this, and then it tells you that it goes to the other side. The linear equation of motion just tells you that you go up. And this one tells you that you go up and down. And then you have to have a full nonlinear dynamics to tell you what then happens. And now you can do different these quench times, and sure enough, you have an asymmetry here, and then it gets cut off somewhere with a quench time between 10 and 20. There's nothing left. Oddly enough, this is a different Higgs mass. You have larger intermediate values, although the error bars are so big that it might very well just be like that. And then I can't tell for sure.
What is your quench time 0?
It's just immediately minus mu squared. Which of course is, well, it's too fast for the dynamics. There's not that much difference between, turns out, this one and this one. They're both so fast that the dynamics don't notice, really. Okay, then you calculate the final symmetry. You put everything in, your lattice, and you take a reheating temperature to calculate the entropy, etc., and you discover that the Faraday symmetry is 0.2 times 10 to minus 3 times this parameter delta Cp. So this has to be larger than 10 to minus 6. Now, if this had been this 10 to minus 20, that's it. End of game. But if it's, in fact, just the Yarskog, which is 10 to minus 5, then you're in business. It's neither. Quench time has to be less than 20, and that's dependent on the Higgs mass. And we have not included it in infinite dynamics. So these guys did that, although they didn't have CP violation. But they could do this asymmetric diffusion in principle. Now, the asymmetric diffusion to so the easy way of interpreting it is because it looks, the term that we put in looks like a chemical potential. Right? So it's basically phi squared, and then there was Chern-Simons number, local Chern-Simons number, say, of x comma t dot delta Cp. That was the term. Phi squared. And that's really easy to interpret as a chemical potential. You do partial integration, this guy goes over there, so then mu squared of t is phi squared dot. So then you can do this. So if this term is in fact the one that comes in a leading expansion of the fermion determinant, everybody, f dual phi diagonal phi, then you're in business. Then you just have to calculate what this prefactor is. Okay. So you integrate out the fermions, you expand the resulting trace log determinant in A's and D phi's, which is called the covariant gradient expansion. It means you have resummed all the phi squared insertion. And then you discover that the coefficient is 0 in this guy. It's unfortunate because we only discovered that after we've done all the simulation. This is the only value we can't use for anything. It means that, of course, the leading order is in fact not leading order. You have to go to a higher order. However, what you do discover is that there are two terms, and one is the FF dual bit, and this has these various Yukawa matrices which will give you the Jarlskog, except that it's not there because the Jarlskog is the trace of 4 V matrices. But here you only get 2, and they always have imaginary part 0, and that's why it's 0. It's a CP range. But the coefficient turns out to not be phi squared. Instead, it's a complicated function of lambdas and phi squared divided by some other complicated function, lambdas and phi squared, which happens to cancel out the phi squared, but instead be something like this, products of these guys in the same way we had before, but divided by similar terms in the denominator. Sums of several of these functions, blah, blah, blah. And it turns out that this, if you put in the standard model values for the Yukawa couplings, you get order 1. This is 0 temperature. Right?
Sorry, so you mean you just have FF dual?
FF dual times
number times the FF
yeah.
dual.
Because so here, you know, we have it's phi squared divided by mass scale, so we had v squared there. But in fact, it's not v squared; it's phi squared, in a sense. Except in this complicated way, it's phi squared. Which maybe is what one would expect. It comes from the fact that your propagator has resummed these phi squared, so it's 1 over p squared plus phi squared. So you have lots of complicated stuff denominated as well. If you would do perturbation theory, your propagator would be 1 over p squared. And okay, then you don't have any phi's in the denominator. But if you do it in this resummed way, have that. And then, so if you would do 1 over p squared, you would get 1 over t squared, presumably. Here you get phi squared. You could possibly get, if you were not 0 temperature, you would get that. Then this cancellation probably doesn't work anymore. But as long as temperature is much smaller than something, then these cancellations work out. And that's the neat bit. And this is big. It's not
so the coefficient is some 1 over n pi squared times j. JCP, right?
Yeah, so the coefficient is j, CP, which is 10 to the minus 5. And then there are various pi's and things.
Right. So this operator presumably induces electric dipole moments.
Yes.
And what are the bounds on the coefficient?
They do not, this is small enough.
Do you know how
we didn't estimate. I can show you that. That's a paper that I'm going to show.
Because the
Yeah.
limits. This will induce electron EDM.
Yeah.
And the limits are going by a factor 100, presumably in the next couple of years.
So Young did an estimate, and with this value that we require, then you're okay. But I don't know by how many order of magnitude.
Yeah.
I don't remember.
And it's an estimate, not a.
Mm.
I mean, you can do a perturbative calculation
Mm.
with that operator, presumably, and get the actual number.
Yeah, there is a paper I looked up. Maybe it's not the correct one, but I can.
Yeah, I'd like to see that.
So why don't we write normally this FF dual term in the for the SU2?
It's a total derivative, so the equation of motion doesn't.
Yes. But so that's the theta
It's like theta
term
QCD.
for QCD.
Yes.
There's nothing that prevents you from writing it down. It just has no consequences normally.
Right. So, but now you are saying that.
I'm saying there's a consequence,
Yeah.
but that if you get it from the fermion mass matrix, it's a zero. That's what I say.
Yes. But so if it has a consequence, then we should write it in the.
Yeah.
Actually, we are free to choose.
But I don't know if you do. So if it's total derivative, can you do? Then you. I don't know what's a boundary term. Maybe you can't do classification motion.
But with the phi dagger, phi, it's not a total derivative.
No,
Yeah,
phi by phi is not.
Yeah.
But if that goes away and it's just that, then you just have F of dual, and then
But the total derivative is just GG dual in QCD. It's the theta term. So
Yeah.
you still have it,
yes,
and you only know it's small because of EDMs.
yes,
Right. So you're saying that the leading, but when you do the leading term in this, when you integrate it out to fermions, the operator is just FF dual.
Yeah. So
And
obviously,
that's zero.
obviously the thing I get from the integrating on fermions is not constrained because that's just the standard model. But if I would introduce it by hand, an extra term, that would be constrained by EDM.
Right. No. I understand.
Yeah.
I understand.
But indeed, you could do that, and you.
But I guess also theta QCD is zero if one of the quark masses goes to zero.
Mhm.
So there's probably a reason why SU2 FF dual is zero in the standard model. And maybe that's what you're seeing when you actually integrate out the fermions, is the reason why.
Could be.
But you say the higher dimension operators are not zero.
Now comes the thing. So then we gave up, right? Because so what you would write down typically for the next order is something like that, f of u times coefficient. But we do know calculate what this is. We don't know how.
Well, you could have the Weinberg operator. You could have a trace of 3 Fs.
Yes, you could also have d phi, d phi, d phi, d phi, d phi, epsilon.
Yeah, but that probably looks like phi squared.
That's very similar. You can
Yeah.
do partial integrations and
Yeah,
stuff.
yeah.
Now, what turns out to happen is, so these guys did it. So these guys and this guy, they were here last week. They actually calculated it. And the answer is that it's coefficient 3 over 8 pi squared 16 m charm squared integral phi d mu phi squared phi d sigma phi squared phi d alpha phi squared phi d alpha phi squared plus some other permutation of these, and then there is d rho sigma mu rho phi.
So that's dimension what? If you don't have the phi squares in the denominator?
A lot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, plus 4. It's 16.
And then divide by phi squared.
Phi squared to very high power.
So the ultimate dimension is what?
Always 4, of course.
Oh, these are always.
And actually this is not m charm squared, it's actually charm coupling phi squared.
Well,
So this is all dimension 4. There is 1, 2, 3, 4, 5, 6 divided by 2.
no, I wonder why you don't get trace F dual.
Oh, sorry, there's an F epsilon here. It's not F of duals. I mean, this is F.
No. I'm saying another operator you could get
Yeah.
is F dual.
Yeah. So it turns out, and this is very surprising, you get hundreds of terms The only one that survives is that one. Once you take, well, yeah. So once okay. So that's what these guys tell me, right?
Okay.
If
Since
you
do
plug it all
calculus,
in,
yeah.
and then you do, you put it into Mathematica, and you do full simplify. The only thing that's left over, but it took him a long time, and he had to massage it a lot, right? Then you get one term. Now, the neat thing is that this coefficient here is 9.87. Because you get, again, many terms of that type. And if you put in the stuff, you get that. You get 10. Which is, I mean, I'm baffled that they can do it, but they did it. So now I have coded a code with this operator. Now also, well, there are some, well, first of all, it's very, it's a hassle to code, right? And it's going to run, it's going to take a month to do one configuration. But I'm going to run it on your computer. So that's okay. It has an issue with phi when phi is 0, because it's divergent. But actually, while we were here, we came up with a way of, we believe that was what I talked about. You put in a cutoff that resolves that, and we think it resolves it in a consistent way. So that's okay. Then you can just go along and do it, and then, well, there are practical issues about whether, we have to run it with sufficiently large value for this guy that we can actually see an effect on lattices of the size that we have. That's something else.
So in that, how many phi's? You have the same number of phi's in the numerator.
Yeah. So these kinds of
it's all the gauge fields that are
these kinds of objects are just a way of writing a mu.
AMUs.
Yeah.
Basically.
So in the end, are there any phi's actually left?
There are, because so this is a mu if you are in unitary gauge.
Sure, but yes. So I mean, are there the same number of phi's?
Yes.
Is it?
But there's two left here.
There's two left.
Two left.
Right. Okay.
But
so
this
it is
thing
similar.
is divergent in itself. Because the derivative need not be 0 just because phi is 0. That is the problem. There may be sort of more. So that was what I discussed with them about. Is this because if this would mean this, it would still be singular, but maybe not divergent. But it is in fact that, they tell me. So it is. So one has to be a bit careful. So but you put in a cutoff here, and because the point is that there are very few. You need the zeros, as I said, but the value of the force at those zeros should not be divergent. That's an artifact of the derivative expansion, because derivative expansion is not valid there. So you should ignore it there. And one way of doing that is to put in a cutoff and say, at these few points, we're just going to cut it off. It's basically like interpolating between the guys next to the zero. And I think that's allowed. So we're working on that. And then, so the guy who invented this.
So what you're saying is you're trying to muck up the effect of the fermion determinant near zero values of the Higgs field by putting some effective cutoff in
I'm saying
that operator.
I'm saying that in the fermion determinant, there's nothing that tells me that it should be divergent at phi.
Right. But you're trying to make it look like a series of local operators in the derivative expression.
Yeah. So so the argument is.
So how do you know in that limit that the higher dimension operators aren't equally important?
Precisely. So the thing is, if phi is close to 0, you would want to not do derivative expansion but field expansion. So then instead, so what you have is that D is in fact this. Something with that and something with this. Right? Now you can either choose to expand in d phi's, d5 of phi square, or you can expand in the other one.
Unless both are, if you're near zero and it's a minimum, then why isn't d phi? Do we know that?
Okay, if you strictly speaking, if you go like that and you touch 0,
Yeah.
then you have 0 over 0.
Yeah. So I'm.
But that's not very likely. Okay, that's true.
Is it, do you really need the field, or do you, I mean, yeah, I guess you do. It's a little dicey.
So the thing is now that what ends up happening is that this thing becomes d phi squared plus d phi over phi squared. If you think of this as being a form that interpolates between an expansion in this parameter and expansion in the inverse parameter, then this is the interpolation. In principle, that could be a constant here. Then this is then what we replace by a cutoff. And then you can estimate, so you can calculate what this object is actually on the average. And it turns out to be 50 GeV. So that's our cutoff. And it works very well. You don't get any.
Do you? I mean, it looks terribly noisy to me, that kind of operator, because it's such a high power.
It is
Of the field. So
but everything is infrared. There's no ultraviolet noise.
yes, but I mean, at some stage you do accumulate
Yes.
ultraviolet noise. You
Then
will
you should-
excite that, and
Yes.
can you then?
That I don't know. But everything is smooth so
Initially,
far.
yes. I see.
Yeah, you do sort of Monte Carlo it then.
Yeah, sure. Monte Carlo is impossible, but I was just meaning, even when you start to heat up,
Yes.
the more you start to propagate into UV. I
Yes.
mean, it becomes noisier and
Yeah.
noisier.
But so for instance, Chern-Simons number, which of course is much simpler than that, is completely smooth all the way to the end.
Yeah.
Also-
just yes, so what's wrong with just doing expansion in powers of phi? Why do you have to have these phi's in the denominator?
But if you don't have phi denominators, you don't get this cancellation I had before. Then you just get perturbative, a good old perturbative thing.
Is it,
So phi squared. So first of all, phi squared
yeah,
is.
so why is this? Why is this better? I mean,
Well, it's a resummation.
yes, but so why do we have to resum? Is there something wrong in the expansion? Does it?
Well,
not work?
the expansion. First of all, this expansion was never really done, right? That was just this order of magnitude. But then you get this, whole product of masses in the numerator. You don't get your Kappa coupling denominator. You get, you get the wrong thing. You get it much too small.
But suppose you would live in a regime where all the lambdas were order 1, so you weren't worried about getting some
Yes.
operator that had the lambdas in the denominator.
Yeah.
I think the question is, in the field theory structure, is there
Yeah.
any reason why you would do this kind of resummation over a conventional resummation?
Well,
it doesn't have the d phi over phi structures.
No, you could. I suppose phi is big, at least at the end. So you might want to say it's not small. And so I mean,
Because the question is how big? I mean, how small is small? and how
so
big
p
is
squared over phi
big?
squared.
What are you comparing with? I mean,
I'm comparing
is
this.
the minimum? Is the there? I mean,
No, so that's the thing.
With the expansion,
if
then
you do-
phi is equal to
if
phi
you
is
do this-
minimum.
If you do this, the expansion is this. It's either that 1 plus d phi over p squared plus phi squared. If this is small, you can expand. And if you do the other one, you will get p squared over phi squared. If this is small, you can expand. Right? And the momenta that you are exciting in the transition are momenta that are less than mu.
So, but I mean, you're writing down a sigma of phi and d phi in your phi squared plus d phi, right?
Yeah.
So why stick there? I mean, in principle, you could have phi. I guess you just want dimension 2, so those are the only things you can write down. Unless there's some other.
Yeah,
stuff.
yeah. So I mean, it's whatever. It's
Yeah,
it's
yeah.
d slash square. Whatever this is.
Yeah, okay.
So this, of course,
Without-
if p, I mean, whether or not this is not small in the beginning, and it's not small at localized zeros. Now in the beginning, we see that there is no CP effect anyway. But later on, I think it's allowed, except when, I mean, yeah, so that, yeah. There's another comment which is that this certainly is not just a chemical potential which ensemble them. Right? There's no reason why this would work with this asymmetric thing. And since these guys now sit together with it, before it was just phi squared, so there was no effect on the phi angles. But now it could. So it could very well be that this would be a force acting also in winding number, in addition to Chern-Simons number. And it might be that this is much more this thing about unwinding, etc. I don't have any good feeling for what this actually does to the equation of motion. But it's certainly much more complicated than that. I would be surprised if there was some simple way of doing that. Anyway, that's what we're doing now, and I even put your name on the slide because we're working on. We decided to have a look at. So there's an inflation model which is going to do a low scale. I mean, you can check out whether you can see that. She always rule out. We're going to have a look at that. So, and then actually, so you know, simulations are now beginning to run with this thing, and it should take a few months. And hopefully, I'll have something to. Hopefully, we can see the signal on the lattice, if the lattice is big enough. If that's big enough. Otherwise, well, otherwise it's too small. Right, that's all I want to say. Enough. Thank you.
Okay, why didn't you have the inflaton field in your simulations?
Because I was too lazy. It complicates things. So I said that there's no resonant preheating, but if it would be there, it would sort of go that way, and the Higgs would go that way, and they mix, and you would, you know, it's just more complicated. You can do it. I mean, these Spanish guys did it, but then they sort of, their focus changed. They wanted to calculate magnetic fields instead of gravitational waves. But you could. Here we just assume that, and it's. I did do a test, and indeed the Higgs field then big.
But that might affect the conclusions in the sense that...
It could. In particular because it's so sensitive with the Higgs mass. If the Higgs mass then changes a lot in time, you could have... Also, it introduces extra energy. Maybe you could test kinetic energy. So, yeah. No very good reason. I also didn't have the U1. Which one could? SU3 and fermions.
In principle, if you included all the standard model fields, fermions and everything, you would have a lot more phase space into which the energy can go,
yes.
And it could affecting things would probably equilibrate faster.
So my guess is that if you include everybody, this would still happen. This would still happen, but this wouldn't happen. It would just be dammed out and decay.
So your first drop in winding number would still be there?
Yeah. I think this would be unaffected, and then it would just stop. And because the thing is, so if you have this other mass, if the Higgs is a different mass, you get that this guy sort of goes up again and end up here. I think that effect might be just sweet.
But then I mean...
Sorry?
Okay. I mean, if the depends on the top. I mean, if the top
quark
top quark sucks energy so fast from the Higgs, so that you never bounce back.
Yeah.
And
so this thing about these Higgs masses, because this guy and this guy, they sort of oscillate a bit up and down. They are correlated, and so when if one is down and one is up, they can easier go through to the other side, etc. And that depends on the ratio of this Higgs to this mass to that mass, which is W mass. So as you scan through that, I mean, whether or not this, because once you get here, you have sort of spherons and they can better go over the barrier if the barrier is low. You can make sort of modeling of how these things go. And then you can reproduce that. In some cases, you can sort of resonant running that way, resonant running that way. But I think that would just be smeared out if you had all the. And then I think this is, and this is, work. But I don't know what it look. I mean, with that operator. So far, the only with that operator, and it's very extremely preliminary. But there's nothing happening here, and then a little bit begins to happen over here. But I really don't know, because the Higgs is very small there. So this thing has high power. Well, was divided by high power. I don't know.
So just to go back, so in this plot, what is biasing the, where's the CP violation? I sort of lost the...
CP violation comes in
Just
this,
in
and
yeah.
then that.
And that's where you just assume some number, not the standard model. Because the standard model gives you, you were using for this the operator that was just 5
Yes.
squared f squared,
Yes.
which is 0.
This is the wrong operator.
Right. So what did you assume for the coefficient of that operator?
I just found it as a I found the result as a function of the coefficient. This is one particular value.
I see, I see.
And then I interpolate too.
Because you could imagine some beyond the standard model physics
Yes.
that integrates out and gives you a non-zero coefficient of that operator.
Yes.
But then it would be suppressed not by the mass scale of the
Yes.
physics, but if it's not so heavy, it might actually be kind of interesting.
Yeah. So actually,
You know,
we
the
tried.
CP violation might not be 10 to the minus 5,
Yes.
so on the other hand, you'll have some v squared over m squared suppression.
Yes.
You might actually be in the game, and then the question would be the EDM phenomenology and what you get from this first
Yeah.
operator.
So we did that in the sense that if you have, for instance, if you have 2 Higgs doublet model,
Right.
you get this term automatically. And then if you put in 1 TeV as the mass scale, then whatever you put as mass scale, the overall coefficient that you need for this to work is always below the EM bound, at least at the time when we looked it up.
Right, right.
Well, that's still the case, I don't know.
So in supersymmetry you do have this term.
Yes.
And
Yeah.
how about at finite temperature? Does it change the calculation? Do you get non-zero coefficient in the standard model?
So I think if you would do the standard model, the best you can do is to do what Shukovnikov did. Because now you have this cancellation denominator. Instead of having the mass, you now have the mass plus temperature.
Yeah.
And then I think then the cancellations mess up and go away. Then I think you again have 10 to the minus whatever.
Yeah.
And now we're sort of in the intermediate range. You start out at 0 temperature, you end up at finite temperature. So it's not even obvious that this completely applies. But there's an argument that as long as your temperature is below something.
I mean, it's certainly true in supersymmetry. At 2-loop, you get the Weinberg operator, for example. So you FFF dual. And so that's a much simpler operator than the
Yes.
one that you're...
Yeah.
I mean, it actually might be sort of interesting, rather than concentrating on the standard model,
Yeah.
to look at situations where you have these lower dimension operators that are pure gauge and that are probably simpler to do the simulations with and study their effect.
So that's something that I forgot to say. So the one that came up with sort of a calculational way of doing this, one of the calculations is this guy Salcedo. And after these guys had calculated it using their method, which is similar but not the same, he wrote a paper where he uses his method, and he says that that term is 0. So you get an effective action, real part, imaginary part. The imaginary part has the epsilon.
Yeah.
That's the one everybody looks at, because it violates P, CP. But it violates CP by violating P. And there's this one coefficient, one term, and this guy says that it's 0, and these guys say that it's non-zero. What he, however, then goes on to say is that in the real part, there are terms that break CP by breaking C. And those terms are pure gauge, only gauge terms. So now, he went in their method and found those coefficients of those terms. And of the terms are, they're a page long and hopeless, and it's just 4 F's in various combinations. So one could do them, but I don't know now, because Chern-Simons number is P odd but C even. So
Right.
what happens to Chern-Simons number if I have C breaking and not P breaking?
Well, if it's an SU2 gauge theory, you've got some parity violation at loop level, so presumably you could still induce that operator.
Yeah, no. So, but if I would do a simulation,
But then it would be C.
I would looking at a p-odd operator with C breaking. I don't know what happens then.
What is a pure gauge operator with C on?
It's all a bit confusing.
I
So,
don't understand what those operators would be.
so these guys don't believe those guys. Well, they do believe that they have found now these. They're not the same terms as they find, but they're similar. And they have different coefficients. So they do believe that there are C breaking terms. But they don't believe that this other one is 0. So they are now they have a bit of a conflict.
So your operator, Salcedo was saying is 0.
Yeah. Actually, so he just says they have sort of a back of the envelope argument for it. Anything in there must be 0, just because of something. But they don't actually try to reproduce their calculation. They also didn't contact them before they wrote the paper and said that they were wrong. So they don't quite believe them. But the formalism is slightly different. But it would be nice to know whether it's 0 before I do that one for a very, very long time.
Yeah, the problem really there is that it is so singular when phi goes to 0, and you have zeros of phi.
Yes.
In your system, and
so that it tells me that this term cannot be used there. It's the wrong term because I used the wrong expansion there. Okay, so that's what. So ideally, if you could sit down and calculate the leading order in the opposite expansion, and then you could somehow interpolate between the two, so that you use one the other end. That would be ideal. If one could do that.
yeah. I mean, because it's it's a sensitive to the direction of the phi, or
Yes.
I mean, if you go to unitary gauge,
Yes.
and there's no direction but the value of the a mu, but it's all kind of muddy when you are very small values of the phi, because you can translate it.
But in order to roll out the model, the mechanism, what do we have to find?
So I need to find the Higgs mass. I need to find the Higgs. If you're done for the Higgs, then I'm out.
Okay.
So what we're looking at now is, so there is also this inflaton in the background.
But you can repeat the same mechanism also without the inflaton.
No.
You need inflaton.
Yeah, I can't quench the mass. So I have to find inflaton, and it has to be at electroweak scales. Although it might be mixing so weakly with the Higgs that it's hard to see, but it should be there eventually. And it should has pretty strong coupling that this quench flip is quick enough. That's it really.
Any signatures for CMB?
There are no, the tensor modes are 0 essentially. So it's very low. So it's low scale inflation. So I think the spectral index you can always fiddle so that you can get it. But if you would find tensor modes, then you're dead. Because energy density is so low. Yeah. So there's no inflaton at that scale. If you find tensor modes,
Yes, but inflow, I think that, I don't know, you need simply a previous symmetry breaking, similar to the symmetry. I'm saying, okay,
Sure.
it's not, you need another scalar.
Yeah. Which has to flip. But it has to flip it at 0 temperature. If you start at a finite temperature, then everything is gone, washed out. CP violation is done. So you really have to be at 0 temperature when you do the flip. Which is why inflaton is the easiest. You have to just come out of inflation. So you might as well use the inflaton. Now obviously if you would embed this in a bigger theory, like symmetry, you have all the fields you need, but then you may also have a first order phase transition, so then you need to do all these kinds of fiddlings with. Indeed.
But you may not. I mean, even in MSSM, first order phase transition is
Elusive.
is marginal.
Yeah.
And so this still would be kind of interesting, because then you could get the CP violation with these simple operators.
Yes.
And you have one principal new light degree of scalar freedom you have to look for. And, well, then you get all supersymmetry.
Yeah. Yes.
So it's maybe, I mean, the other thing you're going to have to find for baryon asymmetry is the CP violation. So if this operator doesn't work,
Yes.
right, you're going to need a non-zero EDM at some point, or a zero EDM to test the CP violation.
Was that there is one other way of doing it, which, well, I wanted to do it for many years, but I'm too lazy to do it. You could just do the fermions, simulating with the fermions.
I was going to say, then you don't have to expand.
You don't have to do an expansion, you just do the fermions. Now the fermions are quantum, and you have to do the quantum modes, and it's numerically hard and everything. At some point these operators are going to overtake the problematics of doing fermions. So then you do classical bosons and quantum fermions, and there is a way of doing that, and one should just get on with it. But one should buy a student and have them do it. And then you can just do it. Of course, then you have a... So you can maximize your mixing. So the largest number you can get out of the CKM matrix by tuning, not using the physical language, but just you can get this, whatever the square root 6, or 1 over square root 6, for J. Make it as big as you want, as you can, and then you simulate and you hope to see something at the lattice. But now you can't get rid of the fact that it's suppressed by J. So you really have to be kind of confident that you see it in a big enough lattice. You can't twiddle delta CP. But I think that would be a way of doing it. And then you have everything. There are no expansions, no divergences, no nothing. Just